Imagine you get the following question in an interview. You are asked to do an in-order traversal of a binary tree. You think, sure, this is easy enough. I could do a depth-first search and it would take linear time and at worst, linear space complexity. But then you get the dreaded question from your interviewer. But can you do better? And since you watched this video right before your interview, you knew about Morris traversal, which allows you to traverse a binary tree in linear time and constant space complexity. Let's first consider how we traverse a tree. With depth-first search, we start at the root, and as we traverse down the tree, we record the path we take. It's like leaving behind breadcrumbs, so we would be able to find our way back to the top. But the issue with Morris traversal is that we are told that we can't use extra memory to store our path through the tree. So once we go to node 2, we won't know how to get back to the top. And without getting back to node 1, we won't be able to find our way to node 3 in the example. So clearly we need to use extra memory even though we are told that we can't. The trick is to use the input tree itself as the extra storage space. Not shown in the tree diagram are all the pointers to null nodes. When a node doesn't have one of its children, it still uses memory to store a null pointer. So we could store a reference to node 1 by overriding one of the null pointers. We could use the right child of the predecessor of node 1, which in this case is node 2. In this way, we give the reference to the top node only to the node that needs it, the node that we visit right before going back up to the top. Another way to see it is if we were to do an in-order traversal, 2 appears right before 1, so it's a clear predecessor. And here's one more example. The in-order traversal will give result 2, 3, 1, 4. So the predecessor of 1 would be 3. To find the predecessor algorithmically, we simply need to go left once and then continue right to the bottom. So 3 can be linked to 1. But wait, you might say, wouldn't this create a cycle in our tree? So when we do our traversal, we would get stuck in an infinite loop. And you are right, but there is a way to resolve this issue. The cycle actually helps us get back to where we were in the beginning. When we visit node 1, we can test to see if there is a cycle. If there is no cycle, then we know we are visiting node 1 for the first time. However, if there is a cycle in the tree, then we can conclude that we have visited node 1 before. So we are done traversing the left branch, so we can continue on to the right branch. Before we move on to the right branch, we simply need to break the link from 3 to 1 to remove the cycle and reverse the tree to the original condition. So to sum it up, the first time we visit a node, we go left. The second time, we go right. When visiting a node, we first find its predecessor to create link to the current node. If we detect a cycle when looking for a predecessor, then we must have visited the node before, so we want to break the cycle and then continue to the right child. If there's no cycle and the left child exists, then we want to make a cycle and go to the left. What if a node has no left child? Then we don't need to worry about this process of creating and breaking a cycle and could just continue traversing onto the right child. And now for the code. I define variable node to be used to traverse the tree. The first node we are at will be root, so node is initialized to root. Then I will define the result array to store the values of nodes in order of in-order traversal. I use the while loop to traverse my tree. So while node is defined, I will execute the following steps. I first need to check whether or not the left child of the current node is defined. If it's not defined, then great, I can just record the value of the node in the result array and then continue to the right. Otherwise, I need to find the predecessor. So for this, I need to define the findPredecessor function. So the original node that I get in my findPredecessor function, I call it root. And I use the variable node to traverse through the tree to find the predecessor. So I initialize the node to be the left child of the root, and then I continuously go right while the right child of the node is defined. And to avoid getting into an infinite while loop because of a cycle, I need to check that the right child of the node is not equal to the root. And then I can update node to be the right child. And once I break out of the loop, I have found the predecessor and I return it. Once we find the predecessor, we can check if the right child of the predecessor is equal to node. If it is, then we have a cycle and we have explored the left branch already, so we can go to the right. So first, I will break the cycle by setting the right child of the predecessor to be null. Then I will push the value of the node onto the result array, and then I will go to the right. Otherwise, if there is no cycle, then we're visiting the current node for the first time. So we want to create a cycle by setting the right child of the predecessor to be equal to the node, and then we can continue to the left. At the very end, I will return the results array. So I'm using Leetcode to run this, so it works, and then it gets accepted. Because it's a little more tricky, I do want to go in more detail through an example. Let's look at the following example. At first, I will initialize my node, and I will set it to the root, and I will also initialize the result array. And then I will get into my while statement. So while node is not null, I will keep running my while statement. First, I check if the left child of the node does not exist using this if statement. Since it does exist, I will need to execute the else statement. First, I will need to find the predecessor. So I will need to run this function findPredecessor. It will have its own variables, and I'll write them in green. So it will have root. And since I called findPredecessor with node 1, the root will be set to 1. And then it initializes node, which will be set to the left child of node. So it's going to be 2. And then while the right child of node exists and it does not equal to the root, I will traverse to the right. The node will go to 3, and then since 3 doesn't have a right child, it will exit and return. And I will have that the predecessor will be equal to 3. Then I go on to check whether or not the right child of predecessor is equal to my node, and it doesn't. So I will execute the else condition. So I will set the right child of the predecessor to be equal to my node, and then I will update my node to go to the left. So the node will be set to 2. And then I will go back to the top of my while statement. Now node 2 doesn't have a left child, so I will execute this if statement. I will record the value 2 in my results array, and then I will update node to the right child. So node will be set to 3. And then I will go back to the top of my while loop again. So in this case, 3 doesn't have a left child, so once again, I will record 3 in my result array, and I will update node to be equal to its right child. which will take me back up to node 1, since I have a cycle here. So this will be the second time I'm visiting node 1, and I will check, does my node 1 have a left child? And it does, so I will go on to execute the else statement. So I will first find my predecessor, which once again will return 3. Now the right child of the predecessor is equal to my node, since we do have a cycle. So what I will do, I will break this connection, so the cycle will get removed. Then I will push the value of 1 onto the results array, and then I will go to the right. So my node will be updated to node 4. And then executing the while statement again, I have that 4 doesn't have a left child, so its value will be recorded in the result array, and then I will go to the right. Since 4 doesn't have a right child, node will be set to null, so I will break out of my while loop and then return my result. So it's quite clear that the space complexity is constant. To show that the time complexity is indeed linear, I will show it with an example. So when thinking about time complexity, you might wonder, why is the find predecessor function not push us to, say, n squared time? Why is it still linear? Suppose I were to run find predecessor function on every node in this tree. Starting at node 1, the find predecessor function will visit node 2 and node 5. Starting at node 2, find predecessor function will visit node 4. For node 4 and node 5, since they don't have any children, the find predecessor function will return right away. For node 3, the find predecessor function will visit node 6, and for node 6 and 7, it will just return immediately. So just from this one example, we see that if we were to run find predecessor function on every node, it will only visit each node at most once. So it will run in linear time. And if we were to run find predecessor on each node twice, it will still run in linear time, because 2 times n still gives us linear time complexity. By changing a couple lines of code, you can turn it into a preorder traversal, which can be a good exercise. Using null pointers in a tree or a linked list as extra memory storage is a useful trick that can help you solve other problems. If you have any questions, please let me know in the comments. Thanks for watching, and see you next time.